that and recording this. Okay, get started. So, hello everyone. As I've been saying for the past 3 weeks, my name is Harry Byers. I'm the project manager for the NASA Student Launch Project for the Buckeye Space Launch Initiative. Today we're going to be looking at using data, and we're going to apply this to aerodynamics. So our goals today are to look at different sources of data that pertain to the same system. In this case, the aerodynamic system of the rocket. We're going to try to understand potential sources of error in a data set. And we're going to try to use the data that we have to gain a little bit of insight about our observed system, which again is the aerodynamic system of the rocket. So we're going to apply this to the rocket design from this past year for the NASA Student Launch Rocket. We're looking at multiple sources of data. Like I said before, we're looking at test flight data from an actual flight, open rocket simulation data, which we kind of already touched on 3 weeks ago, historical data from a textbook, and CFD simulation data. So we're going to start off just in the order that we have currently with test flight data. So on board the rocket this year, we had 2 flight computers, a telemetrum and an Easy Mini. Each really has 2 main sources of data. They both have a pressure sensor and an accelerometer. So the pressure sensor records pressure, which can be directly calculated into an altitude reading. And then we can use the finite difference method to find velocity from that reading, similar to using the definition of a velocity as the time rate of change of a position. So finite difference is kind of like taking a derivative. An accelerometer takes acceleration data, and we can use quadrature, which is a numerical integration method, to find velocity from that data set. What else is useful to take data? Probably want to take a timer data or clock data for time history of these parameters. So we need a change in time to take either an integral or a derivative. We would also like to know at what point do we reach our apogee and how long our flight is and things like that. Thermometer for temperature data, which is important when you're flying for just atmospheric data, understanding how to take that pressure reading into an altitude reading. And you'll see in a little bit, taking that pressure and temperature data into a density reading for applying it to our drag model. And then anything else beyond that really depends on what you're trying to figure out on your specific system, if it's not an aerodynamic system, or if it is, and if you want a little more information than what we're looking at. So we're going to go through our test flight data from our flight this past February. The blue line, which is a little jagged, is from the telemetrum sensors. The Easy Mini line is orange, and the gray solid line is from the open rocket simulation. You can see that they're pretty close. As far as percentage goes, percent error on that maximum value is about 1%, but you can see it's a little shifted. The open rocket model shifted to the right. And then, like I said before, the experimental data from this comes from pressure sensors. Going to a velocity readings, these come from the integration and the differentiation methods on the acceleration and pressure sensors. Again, the blue jagged line is from the telemetrum. The orange line is from the Easy Mini. The straight gray line is from open rocket simulation. Percent error on this from the Easy Mini to the open rocket is about 8%. Notice the jaggedness of the telemetrum sensor, and note that velocity isn't directly measured, it's inferred from other data. And as we move on to this next plot, we have the acceleration data for our flight. Again, blue is telemetrum, orange is Easy Mini, gray is open rocket. You'll notice that the telemetrum is kind of oscillating. We could talk about that in a minute. Notice that the Easy Mini is pretty smooth, but it's pretty different from the open rocket prediction, even though the maximum values from Easy Mini and the open rocket simulation are pretty similar. You can see that the profile is pretty different. So let's jump into just using the data right off the bat. What can we use this data for? Say we want to know our drag coefficient. We want to know how much is the air slowing us down, With that information, we can understand like how high are we going to go when we simulate. So sure, if you're an aerospace major, you've probably seen this formula before. It's just a drag formula. So 1/2 scaling factor times rho, which is our atmospheric density, times the velocity squared, times our wetted area, times our drag coefficient is our drag force, which you can use Newton's laws, F equals ma to find our acceleration, and then integrate that into a model to find our position over time. So let's use our test data to determine the drag coefficient. So we're going to rearrange that and find CD. And we're understand that a drag force, like I said before, F equals ma, D equals F. Drag is a force, so we can take a mass times an acceleration. And so from our flight test data, I took this from the Easy Mini sensor because it was pretty smooth. 4 seconds from liftoff, we found our velocity is about 152 meters per second. Acceleration is about 18.5 meters per second squared. That is slowing us down. Our dry mass, so without any fuel on board after we've burned out, we're looking at about 13.5 kilograms. Our wetted area for a little over 6-inch diameter vehicle, it's about 0.188 meters squared. And air density, again, using a temperature reading and the pressure reading from the barometer, we get 1.23 kilograms per meters cubed. Plugging that into the formula above, that gives us a drag coefficient of 0.09. So right off the bat, I mean, looking at that, does that make sense? So let's look at the open rocket simulation to kind of compare to our test data. So open rocket can return drag characteristics for our flight profile, but notice there are different contributions to that drag. So what we're looking at specifically is pressure drag, friction drag, and base drag. We'll talk about those in a minute. And we also have our total drag, which is what our calculation from before is trying to get. Total drag being the sum of all of those other contributions. And you'll notice that our total drag should probably be around 0.5. And we're going to go through and we're going to look at the flight profiles again, just to kind of see maybe where that difference comes from. So here in our altitude readings, it's not too obvious what could be going on. Like I said before, the open rocket simulation's a little shifted to the right. What could cause that? We can talk about that in a minute. Our velocity, which is an inferred parameter of our vehicle's trajectory. The Easy Mini looks pretty smooth, but it's, like I said before, 8% off of our open rocket prediction. Telemetry data is pretty noisy. It looks like it's kind of cycling there. And then our acceleration data, again, the profile of the Easy Mini and the open rocket data looks pretty different, even though the Easy Mini data is smooth, while the telemetry data is very noisy. So yeah, like I said before, it's way different. Open rocket suggests that our drag coefficient should be around 0.5. So why does our experimental result differ? So our sensor error is a source of error from our experiment. So how accurate are our sensors? Are they picking up something else? So the Easy Mini, as we saw, was pretty smooth, even on the acceleration plot. However, the telemetrum was oscillating. Someone suggested to me before that the source of that oscillation could be a structural oscillation. So however it was fit inside the rocket could have been vibrating after burnout or during burnout or during motor burn and continued to vibrate after that. And it could have caused that noise. If you go in and look at the numerical values of the data instead of just the plots, you could potentially find sensor saturation. So if your sensors can only read 5 meters per second squared of acceleration and you're hitting 18, obviously you're not going to be able to capture that 18 in your sensor data. If your sensor's not accurate resolution wise, so it's kind of like, if you're trying to measure millimeters with an inch ruler, you're probably not going to be very accurate unless you understand the relationship between those. Say your ruler only has a resolution of 1 inch, you're trying to measure quarters of an inch, you might be able to do it, but you probably won't be very accurate doing it. Model error. So how accurate was our model? Are we missing something in our model? So you saw the model, it was D equals 1/2 rho V squared A CD. Is that model good enough to capture the full behavior of the rocket at that point in time? And then how can we do better? And then segueing into that, let's look at historical data. So historical data can provide insight to our current problem through past experiments and conjecture based on those experiments. So measuring, the drag on a cone at various velocities and various temperatures, maybe we can find a trend for geometry in case we have something completely new, and we can infer based on our old data, what should we expect to see with our new data before we actually test it. So we're going to use Horner's textbook, which is fluid dynamic drag, to see what we can find. This textbook's from 1965, so it's a little dated, but it's pretty good because it's filled with theory and statistical data on missiles and other aerodynamic bodies, which is, I would say, pretty close to what we're looking at here. And then using knowledge that we already know about our own system, how can we use Horner's resources to infer more information about our system? And then maybe we can talk about a little bit of, have we seen historical data used before? I think on a team project like this, when you're trying to figure things out on your own, you can kind of lose track of the different resources that you have available to you. I know we've used Anderson's flight textbook, which is actually, for a lot of boundary layer discussions, is full of historical data. There's a lot of historical airfoil data at the end of that textbook. Just like this textbook that we're going to be looking at has drag data on a lot of different geometries. And you're more likely to see that in class. So let's talk about contributions to drag. So in general, that's going to be dependent on the speed through the flow, your flow speed, geometry of what you're looking at, and the viscosity of the fluid that you're going through. And that kind of gets all tied together in as a Reynolds number dependence. A lot of it's dependent on pressure distributions over your body. It's dependent on your flight regime, subsonic, transonic, supersonic, again, how fast you're going, and the behavior of the flow at those speeds. First, we're going to look at friction drag. We're going to talk briefly about it, only on this slide. It's caused by airflow that's tangent to the surface. So think, a classical physics problem where you have a mass moving over a surface and there's a friction coefficient. You can find a skin friction coefficient for your body moving through flow. And that will tell you how much is the air slipping by my body, slowing me down. It's based on the textbook, from what I've been able to find, it's really hard to just kind of look at the textbook and estimate what this should be. And you'll see that as we look at the pressure drag and base drag, that you can kind of do that with some level of confidence, at least enough to verify some models. Open Rocket, however, suggests that this contribution should be around 0.25 for our vehicle. If you notice that our total drag was around 0.5, so that kind of corresponds to about half of our total drag comes from this friction drag. So it is pretty significant. It's just a little harder to predict. And if you actually go through the textbook or another fluid dynamics textbook, there's a lot of discussion about how to figure out what this drag is. Something we're going to talk about a little more in depth is pressure and base drag. So starting off, pressure drag is drag caused by flow perpendicular to the surface of our vehicle. So similar to before, it depends on all those different flow conditions and your vehicle geometry. And for our vehicle specifically, we're going to look through the available trends and guess about what we should be seeing. Below is a graphic of cylinders in flow. There's 4 cylinders there. There's a flat plate, and there's kind of a teardrop shape. So you can see a laminar model on the far right, or far left, I apologize. Let's see the streamlines of the flow look like around that object. Second to the left, you could see a little bit of flow separation, and continuing on down for different characteristics. So pressure drag is really you can think of it as the difference in pressure from the front of your vehicle to the back of your vehicle. If you have a higher pressure on the front or on the nose of your vehicle, it's going to be pushing back. Whereas if you have a lower pressure on the back of your vehicle, it's going to be pushing forward, but not as much as the pressure on the front is. And if you're looking at net forces, that's going to be slowing you down instead of accelerating you forward. And you can kind of see that in these geometries below, where, let's look at this third one. Oop, apologize. Right here, you have flow going directly into the nose of this cylinder, and on the back, it's kind of separating, and you have little stagnation points behind, which would cause low pressure zones, which we'll see in a bit. Oh, I apologize, I hit a button. Oh no. We're back. Okay, so we're gonna look at our nose cone. Again, we use a von Karman nose cone. And if we actually go into the open rocket model and zoom in, or if you take a physical measurement of the nose cone, we can find that at the nose itself, the very tip of it, it's about a 14-degree half vertex angle. And conveniently, in Horner's textbook, there is a plot here, which I've pictured on the right, that we can look at cones and their half vertex angle and get a pressure drag coefficient for. So von Karman nose cone isn't quite the same as just a cone. So Nate says, why do we use a von Karman nose cone? Correct me if I'm wrong, Nate. A von Karman, so, okay, let me start. There's a couple of reasons why you might want to use it. The reason why we used it was convenience, because we had a mold for von Karman nose cone.
Okay, that makes sense. Because yeah, going off of just memory, I don't think von Karman actually offers too many benefits in the subsonic regime. Like supersonic is by far like the most efficient.
Right.
That's why we use it on the spaceport American rocket. But I
so
think
this year it was out of convenience because we could save a little money on materials and making a mold to use. So we did use a von Karman nose cone this year. An ogive nose cone is, yeah, like you said, there's not really a lot of benefits for when you're avoiding, you're trying to optimize a vehicle for supersonic flight, and you're not really as worried for subsonic flight. Von Karman nose cone, I believe it minimizes drag over is it a volume or an area?
I don't remember exactly what it is.
So experimentally, it was found, and there's probably a actually full-on derivation for it somewhere that shows that it will minimize drag for. I'm going to go with area, but I'm not quite sure off the top of my head.
Yeah, I forget exactly what it was. I know about 3 years ago, the Aerodynamics team for 30K looked into it, and that's why they chose von Karman for the 30K rocket. But they also looked at like all the flight regimes, so subsonic, transonic, and supersonic, and von Karman just happened to be the best like throughout all of them, or it was just kind of like the best of like all of them. It was just performed pretty well.
Sure.
But I think in subsonic, I think we used ogive on the 10K last year just because it was.
We did do that.
Yeah.
And Todd has suggested, because we're not even going transonic this year, to use an elliptical nose cone.
Yeah, you could do that.
And it really comes down to manufacturing ease and what you're looking for. But pressing on with what we have, we can probably try to approximate this as a 14-degree cone. So I put a little red circle there on the chart. I don't know if you can see it that well. It's looking like our pressure drag coefficient should be around 0.1 to 0.2. And if we go into the open rocket simulation, it actually suggests that our pressure drag coefficient should be about 0.11. So it tells you that the open rocket guess is probably pretty close to what we would expect to be seen. But we can further refine our guess. And we're going to look at base drag next. So base drag is similar to pressure drag, except it only acts on the area on the back of your rocket. It is kind of caused by that sharp cutoff and result in flow separation at the end of your vehicle. So again, Horner has a nice chart that we can look at. This is for two-dimensional bodies, so infinite in one direction, but we can try to look at it for relatively close estimations of what we should be seeing. So on the x-axis, we have our four-body pressure drag, which we found to be between 0.1 and 0.2. So we're going to look at 0.2. And then we can see here that we're looking at around 0.15 to 0.25 for our base drag coefficient. So what this is telling us is that we should expect our base drag coefficient to be higher than our pressure drag coefficient. And OpenRocket suggests something similar. It actually suggests something about 0.17. Moving on, we can even like refine this guess a little more. Second, yeah. In another chapter of Horner's book, he actually looks at the backs of missiles. So for people on the team, this might look similar to where this NASA rocket looks kind of similar to the first rectangular geometry shown, whereas the spaceport rocket looks maybe like something below it with a tapered end as we go into the motor casing. So these charts, as you can see there, is for a Mach number of 0.8, so a little more transonic than we're seeing. We're seeing 0.6, but maybe we can relate the two because they are both subsonic, which is what we're flying at. And if you see right off on that graphic, the suggested base drag is about 0.17, which is just what the OpenRocket model says it should be. But you can also see that there's a four-body pressure drag of 0.14 listed there. And then one step further, we can look at the Reynolds number of our flow. So taking the Reynolds number that OpenRocket suggests based on the weather conditions of the actual test flight day, the geometry of the vehicle, how fast we were expecting to go, it suggests that we should be around 30 to 40 million. Conveniently, Horner has a historical data set that talks about, quote, straight missile bodies, which is exactly what we have for the NASA rocket, at a Reynolds number of around 30 million. And this chart suggests that our base drag should be around 0.15. So it's looking like OpenRocket was probably pretty accurate in the estimation. So recall that OpenRocket was saying our base drag should be around 0.17. And then because of our base drag being around 0.15, and we had a range that we were estimating between 0.15 and 0.25 for our base drag, and we're on the lower end of that range, we could probably safely assume that our pressure drag is also at the lower end of that range. We were looking at 0.1 to 0.2. If I actually go back a couple slides, you can see that the lower our four-body pressure drag goes, at least there, maybe we're looking at the same area for our base drag. Moving on, finishing up the historical data discussion. So what did we find out? Friction drag is a little harder to guesstimate, like we did with the pressure and base drag. We didn't really plug in any formulas to find those drag coefficients. We just kind of estimated based on that data. I believe in the textbook there are curve fits to those. So if you had something a little more concrete to play with, you could plug it in and directly find something. We found that our pressure drag should be around 0.1. OpenRocket suggested 0.11. Base drag should be around 0.15 to 0.17. OpenRocket suggested 0.17. So it looks like OpenRocket was doing pretty well for those predictions. Going off of, can we assume the friction drag is accurate without going back to the historical data? We can look at our experimental trajectory data. If I go back a couple slides, we can see that. You know, the main point of trying to figure out what our drag coefficient is so we can predict what our maximum altitude is going to be. And you can see here that our altitudes were within 1%. So maybe we can assume that the 0.25 estimate from OpenRocket is fairly accurate for our friction drag. What does this tell us about our experimental drag value? If you recall that we got 0.09 and OpenRocket's prediction of 0.5 and the historical prediction of something that's probably similar to that 0.5, that's pretty different. You know, we're only looking at 20% of that total drag. It tells us that our first model is probably bad. It's probably a little more complicated than just plugging into that one-dimensional drag formula. Open Rocket's model is probably okay based on the trajectory results like we just looked at, and based on the historical data. We kind of verified the pressure drag and the base drag estimation from Open Rocket here. So it's kind of suggesting that maybe we need a more complex model to find these values. So going beyond, what if we don't have historical data for our proposed design, or if we want another source of information to validate these results, we can do CFD or computational fluid dynamics. So using our design geometry, we can build a CFD model for our vehicle at a predicted flight condition. And then here's some information so we understand what we're looking at. The maximum Mach number predicted by Open Rocket is about 0.64. Again, in that subsonic regime, it's not even transonic yet. And the drag coefficient that we're looking for is around 0.5. We're looking at 0.53. So before I move on, I want to say that Ed on our aerodynamics team did a nice job on pretty short notice building me a CFD model, because I don't use ANSYS, but he does on the aerodynamics team for the spaceport. So he actually did 2 simulations. He did a laminar flow prediction and a turbulent flow prediction. So this is the Mach contour of our vehicle at that flight condition we talked about. And do these results make sense? They kind of look like they make sense. So on that nose cone, you see an acceleration of flow like you'd expect to see on an airfoil as that flow curves around that geometry. You can see the flow slowing down as it kind of goes around the body. And then at the end, you can see a huge slowdown at the base of the rocket. Again, so looking at that base drag, you see kind of like a stagnation region as we slow way down to essentially 0, looking at the Mach number of 1 times 10 to the negative 5. It's pretty small. Does this make sense? I mean, looking at our maximum Mach number, 0.75 versus the 0.65 that we expected to see in our free stream. Moving on to the turbulent model, you see kind of similar behavior. You see high pressure on the nose, you see acceleration over the curves, and you see separation in the back. But notice that our maximum Mach number is pretty close to the free stream at 0.65. And going back between the two, we could see in that base zone on the laminar model, the flow actually speeds back up behind the rocket, whereas in the turbulent model, it stays slow. You could see the boundary layer in both models. So that slow region really close to the surface of a rocket. You can see the boundary layer there. So kind of pointing that skin friction drag. Going on, we talked about pressure distribution being important on our drag characteristics. So here we could see the high pressure at the front of the rocket. And as I'm saying this, I realize I said there's a high pressure on the front of this contour. That's actually the flow slows down when it hits the front of our vehicle because it has to move out of the way. So I apologize for that. But here we can see a high pressure on the nose. Here on the back of the rocket, we can see that there is the blue zone, the low pressure zone in the laminar flow regime. So like I was saying before, pressure drag, high pressure on the nose, low pressure on the aft end. Net force is pushing us backwards for the turbulent model. Again, high pressure on the nose, low pressure on the back end. Looks pretty similar as far as distribution goes. You can see that there's a little bit of difference, such as the turbulent model not having a high pressure zone right in the center of our geometry on the back end. And we'll talk about that in a little bit. Do these results make sense? They seem like they make sense, right? From what we would expect to see, it looks like those contours would probably make sense. However, the drag coefficient data from both of these models are kind of surprising for maybe we would expect to see with those contours. So the laminar drag coefficient model is 0.05, whereas the turbulent drag coefficient model is 0.007. So that's looking at about 50% to about 10% of our experimental drag coefficient data. So what is that telling us? Is that telling us that the open rocket model's wrong and all that historical data is wrong? Or is it telling us that maybe our model's not set up quite right and our experimental model was pretty bad too? And why would we see those differences? So if we set up a bad model, we get bad data, right? So our experimental model, we kind of already talked about that it's probably bad based on the historical data and based on what OpenRocket was suggesting. And why is that? It's not that Ed did a bad job. I think Ed did a pretty good job building this model. But CFD is pretty complex. I mean, you can take a whole class on it. And I believe Ohio State offers 2 classes, one of the actual theory behind CFD and one of actually using the software to build these models. So for this model, Ed was telling me, he did a 2D axisymmetric model. So he drew a profile of half of our rocket and rotated it about an axis. And that's why there's no fins on our contour plot, because if you drew those fins in, it would kind of build a huge geometry around our rocket, which is not accurate to reality. You know, cutting the fins off, we would expect a similar drag behavior as opposed to having a solid revolution of that huge fin geometry around the back end of the rocket. The residuals of the model, Ed was telling me, weren't great. Residuals being the kind of error in our calculation or the differences in the results between our model iterations. So as we further refine the calculations and what we expect to see and know based on our model derivation in theory about that, those should be getting smaller and smaller as time goes on. He said they were pretty large, meaning that they were greater than an order of magnitude of 10 to the negative 4th. But then it's also important to note that a small residual doesn't necessarily mean that your model's correct. Your parameters may be off. Your model might just be wrong. So going back off of that residual discussion, a small residual might not be indicative of a good solution. Nate's talked about it before. I've kind of brought it up that our rocket, the NASA student launch rocket, only goes subsonic, and I would not even consider it transonic. This is built using a supersonic model, which is used for the spaceport rocket. So we're kind of taking that supersonic model and applying that to a subsonic situation, which you're going to run into some issues there because your methods of solving and the things that you're looking for are a little bit different. You know, again, the model could be wrong. Laminar versus turbulence, there's a reason why Ed did both of those, because they provide different results. And depending on the actual conditions of your flight, you might lean towards one or the other. Your turbulence model might be wrong. You're probably not in completely laminar flow. 2D axisymmetric, you know, our rocket is 3-dimensional. You can't really build a 2-dimensional rocket in real life. Things that go along with any computer-aided engineering project, so mesh sizing, the domain around our geometry. So if I go back to those contours, the domain being the rectangle around our geometry, where that flow is actually being evaluated, because there's no flow inside of our rocket, it's only outside. At least we hope there's no flow inside of our rocket. It's just kind of balancing all those things. Understanding what you're looking at, understanding your model really well. So a lot of these things could have kind of played into those results that we got from our CFD analysis being wrong. And I say wrong being that we probably think they're wrong based on the historical data and based on what OpenRocket was saying and based on things that we observed in real life, even if our analysis of the data itself into a drag coefficient was also wrong. How do we improve this model? So again, if you're designing something or you want kind of more concrete numbers to work with instead of those ballpark 0.1, 0.2, we can look at well-known solutions. So I discussed it before, you know, Anderson's Intro to Flight textbook has airfoil data at the back. You could build a model around that. You could build a model around some of Horner's data for missiles, and you can try to recreate those in your CFD model, especially if those models are looking at similar flight regimes to what you're going to be experiencing. And then you can fly your model or test it in a wind tunnel or do some physical tests to it and look at what you observed versus what the simulation is giving you to see if your model's correct or if it's accurate enough to where you really don't care about those small discrepancies. Moving forward, you can use you should be using a combination of these different information sources. So the real world data, historical data, simulation data from OpenRocket, simulation data from CFD. You could write your own simulation to build a best guess at these parameters. And that's kind of the point about why we go to school for 4 years. We're looking at these theoretical design points so that we can better tune our design to act the way that we want it to act. You can build a better CFD model. So, and what that would do for us is that lets us inform our design decisions, and hopefully from that model, we would observe similar results in the real world once we actually build those designs. We could get better hardware for data collection. So I talked about, maybe my sensor isn't very accurate. Maybe I can only get an altitude reading within a meter, which is fine if you're trying to be within, 1,000 meters. Then who cares if you're, 0.1% off of your actual. But if you're trying to fine tune these or optimize your vehicle or optimize your design, you're probably going to want something better. Better hardware. We talked about why was our acceleration data on the telemetrum super noisy. It was suggested to me that there is structural noise. So the accelerometer might have been picking up a vibration in however it was mounted inside the rocket, and that was showing up in our flight data. So you could, look at the design of that, make that more rigid in the body or less rigid, depending on what's going on, actually. And I think that might be all. I actually don't have a question slide this time. So I guess finishing up, there's a lot of things that you can do. There's a lot of different sources of error that you can look at. And you should be kind of conscious of those different sources of both error and information and what you're trying to do and understanding the problem at hand. We looked at aerodynamics specifically. You could fit this to anything else. Like if you're trying to model, let's say, I think something that's been popular was a gamma ray detector that we put on the rockets. What would you expect to see versus what do you actually see, and why are you actually seeing that in real life and it's not in your model? I know Joe has been doing something with vibration on the rockets, so maybe that accelerometer is shaking around. Hopefully that won't be a problem in the future, and hopefully Joe can understand or help the rest of us understand why everything's vibrating or what exactly is vibrating and how. So I'm going to open it up to questions or discussion. Any thoughts? Anything else to add to this?
I don't have too much more, but I think, going off of what you said on the last one, I think a big part of it is like not having fins on the CFD. That's a big reason why you need experimental data, because CFD is one of those things where it's really hard to trust unless you have a model that is like verified and has been tested against like experimental data. So, that's why we do test flights.
Yeah. And so, moving with that discussion of fins, maybe a reason that our CFD model was only about, 10% of what we expected to see. Maybe the area of those fins greatly impacts the skin friction drag. And our CFD model didn't have any fins, so it wasn't capturing that skin friction drag. So,
not only that, but you could also have, it's real life, so you get wind, so you could have
right
drag off the fins. So there's just so much.
There's a lot, but
yeah.
Looking at a simplified model, you could see that the pressure drag that we saw was going to be about 0.1, and we saw 0.05 from the CFD model. It was like, okay,
yeah,
maybe it's capturing pressure drag, but it's not capturing friction drag or something like that. And that just goes into an incomplete model. And if you want to go further, like you were saying, there's wind in real life. So you're not always going to be going straight up and straight down. You might be turning a little bit, and that's going to affect your flight, and that's going to increase the drag that you see.
If you're taking data based off the accelerometer data, if you're not going straight up, you can't really trust the accelerometers. You have to go off of pressure stuff.
So I'm going to rebut that a little bit. I would argue that if you're not going straight up, you might not want to trust your pressure data.
No, yeah, you're correct.
Yeah, the opposite. So you're going to want to take,
You want to know what your sensors are actually measuring. You can't
Right,
just
and
yeah.
that's kind of what we talked about before. Is it really depends on what you're trying to learn. So maybe for like a baseline pressure and acceleration, it is probably okay.
Hmm.
But if you're, if your rocket's not as stable as you'd like it to be, and it's turning over, and it's, going 60 degrees into the horizon like it did last year, then you probably want to know the orientation of your rocket and uh, maybe try to guess at what your velocity vector is. Instead of treating it as a scalar quantity, a vectorized quantity.
What is the accelerometer? Is that a 3-axis accelerometer, or is it
So it
just
depends
vertical?
again on the hardware that you're using.
Yeah.
So, I can speak for our flight computer. The telemetrum only has a one-axis accelerometer. It only
Yeah.
looks at the axial acceleration. So if
Mhm.
you're turning and you have a significant side slip over your vehicle, your pressure, you might be going up, and your velocity vector might be 10 degrees off vertical, but your actual orientation might be 11 or 15 degrees off vertical.
Mhm.
Um, and now your axial acceleration is not indicative of what's actually happening.
Mhm.
So you're going to have to look at that and look at your equations of motion, look at the model that you're building, um, and try to fit that data to that model. OpenRocket uses 6 degrees of freedom. I know RockSim does as well. I think things tend to use 6 degrees of freedom, XYZ movement, XYZ rotations,
Mhm.
three-dimensional movement and rotation in our three-dimensional world. So it's important to capture that if you're trying to look at this a little more in depth. Does anyone else have any questions or want to discuss anything? So maybe I can talk about OpenRocket's model. We found that the historical data suggests that it's probably okay, and we saw that from our trajectory plots that it was probably okay. Um, so OpenRocket does have, it's open source. Its documentation is free to grab. And in there, it does describe the 6 degree of freedom model that it uses, and it describes how it calculates the drag based on your geometry. Um, and I mean, we could see if we go back to look at our acceleration. So drag to acceleration is probably the most direct form of comparison we're going to get. Um, Ignoring the telemetrum data, let's look at the easy mini data.
Mhm.
Um, once we get past burnout, so once we're past about the 5-second mark, you see that we're actually pretty similar when we're coasting versus when we are just starting to burn out, right? So anything below 0 is, of course, drag. We are slowing down here, but once we kind of maybe equalize there in this regime, you can see that the OpenRocket model was pretty similar to the Easy Mini model. So it would be good to go through and look and understand how the rocket's moving in that simulation, because it seems like it's capturing pretty well to our flight. We did get lucky. Our flight was pretty vertical. I'd probably say it's within 5 degrees of vertical, which is pretty good. And again, that's kind of playing back into the previous discussion of, well, if your rocket's a couple degrees off vertical or off your velocity vector, you have to start understanding the limitations of your sensors. This is saying that, well, maybe our sensors were okay for this specific flight and what we observed. But what I was going to say is go into the OpenRocket documentation, understand the model, understand the math behind. So if you are using a 3-axis accelerometer and your rocket flight is not quite nominal, not quite vertical, then maybe use that as a guideline to fit the data to the model and see maybe what actually happened. That's another resource other than just Horner's textbook or other than just, a generic flight dynamics textbook, because it will be a little more related directly to the application of a rocket in flight. And any more questions or discussion points or concerns or anything like that?
I got nothing.
All right. And with that, unless a question comes through right now, I'm going to go ahead and close this out. So again, thanks for tuning in. This was the last workshop of the semester, so hope finals go well. Good luck. And thanks.